Algebra 2, Chapter 9.2, exercises 13 through 20. This is our ongoing lesson, subsequent to exercises 1 through 12. We are graphing and transforming rational functions. In this section, we are graphing them. And I like this section of exercises in that it follows up nicely from what we did pretty recently in the course, which was polynomial division. So we're going to rewrite the function form g of x equals a times quantity x minus h plus k, and it gives you an option of the 1 over b method, but we're going to stick with this method, the a method, as opposed to this one here, just because I think that this first method is easier to work with. So the first thing we're going to do is get this function g of x equals 3x minus 5 over x minus 1. This is a quotient of two functions, and we're going to get this in what we call standard form, which would be like this first form mentioned here. And to do that, what we did in chapter 7 of the book, I think it was 7.4, was polynomial long division and synthetic division. Well, for synthetic division, which we're going to use here, is we take the value of the 0 of the divisor in the denominator, which is 1, and then we put the terms of the numerator here, which are going to be 3 and negative 5. And we bring down this 3, and we get 3 here. 1 times 3 is 3. Negative 5 plus 3 is negative 2. So what this is this translates into, I'm going to put an equal sign here, this translates into 3 minus 2 over the divisor x minus 1. And if we're going to write this in the standard form, that would be, I'm just going to call this g of x also. G of x equals negative 2 is our value of a times 1 over quantity x minus 1 plus 3. So in this instance we have h is equal to 1 and k is equal to 3. And this comes from this standard form that h is the value that shifts, translates the function left or right. A is the one that deals with the vertical compression, or in this case we have negative 2, meaning that we're going to have an upside down reflected about the x-axis type of situation, and k is the translation. So for this situation, the center, which we're going to use to graph, of this rational function is going to be the point h comma k, which is going to be 1 comma 3. So that means that x equals 1 is going to be our vertical asymptote for this rational function. So that's our vertical asymptote. And our horizontal asymptote is y equals 3. So horizontal asymptote, y is equal to 3. So now we can concern ourselves with what this function is doing. We have a being negative 2. So that means if we take a point 1 comma 1, which would be 1 to the right and 1 up from the center, and we stretch by a factor of 2 and reflect about the x-axis, that's going to if we multiply by -1, we're going to go ahead and rotate about the horizontal asymptote and then stretch by a factor of 2, or you could stretch by a factor of 2 first, like this, and then rotate down like this. But in either case, what it's going to do, it's going to give us a point, which is going to be, it looks like 2, 1. That's going to be one of the points. And then as far as the other point, we're going to have, it would occur to 1 to the left and 1 down. And so we would stretch by a factor of 2 and rotate up here. So we would also have the point here graphed, which would be 0, 5. And one way you could also analyze this is to create a table. If you have like x, g of x, you take one value to the right of the vertical asymptote, which is 2, and one value to the left of the vertical asymptote, which is 0, and just plug in and see what you get. And I hope you can see that if we plug in 2, we get 1 over 2 minus 1, or 1, so that would be -2 plus 3, which would be 1. If we plug in 0, we would get 1 over -1, and 1 over -1 is -1 times 2. That's going to be 2 plus 3, or 5, which corroborates where we were earlier. So now we're in good condition to graph this rational function. And to do that, it's going to come like this. That part of the curve to the right and down. And then we have this other point here, 0, 5. So we can, it's going to go like this. There it is. So there we have the two pieces drawn in. And so we've changed the form right here. This is our form, our new form. We've graphed the form. We said also state the domain and range. So our domain, and we're going to use the three different types of notation, inequality notation. We have x is greater than the value of our vertical asymptote than 1, and we have x is less than 1. We have in set notation, x is an element of all real numbers, comma, but x cannot equal 1. And finally, in interval notation, we have x is greater than -infinity to less than 1, union 1, comma, infinity. And the range is a very similar thing, except the critical number here is going to be the value of the horizontal asymptote, which is y equals 3. So we have our range is going to be x is greater than 3, and also x is less than 3. And in set notation, we have y is an element of all real numbers, but y cannot equal 3. And finally, in interval notation, we have greater than negative infinity to less than 3, parentheses union, greater than 3, less than positive infinity. So there we have our domain and range, and the graphing, everything done. Let's go on to the next odd number problem. Before I do that, what I would recommend you do with 14 in order to use synthetic division is, the problem in the denominator here is we have 0.5x, which will complicate things. If you go ahead and multiply both the numerator and denominator by 2, this is for problem number 14, you're going to get, now in the numerator, 2x plus 10. In the denominator, you're going to get x plus 4. And this version, where it's 1x in the denominator as the divisor, that's going to be easier to work with. Okay, next odd number problem that I'm going to work out here is this one. So again, we have a quotient of 2 linear functions, and I'm going to use, as we've done earlier, synthetic division to get this into a standard form. I'm going to put the value of the 0 here to the side of my synthetic division bracket, which is 2. And then the coefficients on the inside, we have negative 4x plus 11. We bring down the negative 4. We get 2 times negative 4 is negative 8. And then 11 minus 8 is 3. So what we get here is, this is going to be equivalent to negative 4 plus 3 over our divisor, which is x minus 2. And to get this into a more conventional standard form, I'm going to write this as g of x equals 3 over x minus 2. In fact, what I'm going to do is I'm going to write that 3 on the outside to be a more conventional place of a. So a, which is 3, I meant to put 3 there, 3 times 1 over x minus 2. On the outside I'm going to put minus 4. So here, the center of this rational function that we're graphing is going to be the point h comma k, which is going to be 2 comma negative 4. So we can mark these in our graph. So we have a vertical asymptote at x equals 2. So here, just kind of sketching it in. So x is equal to 2. And we have horizontal asymptote at it's going to be y is equal to negative 4. So that's our horizontal asymptote. And our vertical asymptote is x equals 2. So for a standard parent function, our point 1 comma 1, which we would normally see, would be right here. But this a value of 3 means we're going to stretch by a factor of 3. So we're going to go ahead and multiply that by 1, 2, 3. So this is going to be one of our points here. which is going to be, looks like 3, comma, -1. And then this other point down here, which is going to be, it would normally be the point -1, comma, -1. We're also going to stretch this point by a factor of 3 from the location of the horizontal asymptote. So 1, 2, 3. So this point is going to be 1, comma, -7. And to verify, we can set up a table again like we did for problem 11. So if we have x, g of x, 1 unit to the right of the vertical asymptote is going to be 3. 1 unit to the left of the vertical asymptote is 1. And just see what we get. If we plug in 3, we get 3 times 1 over 3 minus 2, so that'd be 3 times 1 minus 4. So 3 minus 4 is -1. If we plug in a value of 1, we're going to get, in the denominator, we're going to get 1 minus 2, or -1. So we have 3 times -1, or -3 minus 7, -7. Check. So now we're in a good shape to graph. So I'm going to graph the lower left corner first. This point here is what we're going to go through. And also, because of the symmetry of the situation, I'm going to put another point we're going to have to go through here. So the thing's going to look like this. Here's the curved part. There. And now the upper right corner is going to look like this. Let me remove that one a little bit here. I think I can do it a little more neatly than that. Yeah, it's a little better. So anyway, that's the graphing of it. And so we've found the standard form, if that's what you want to call it, the parameters of transformation. And now we're going to look at the domain and range. Domain, the domain is going to be in inequality notation. Our vertical asymptote is x equals 2. So we have x is greater than 2, and we have x is less than 2. And then in set notation, we have x is an element of all real numbers, but x cannot equal 2. And finally, in interval notation, we have -infinity, comma, 2, union, 2, comma, infinity. And range is going to be the same type of notation. And our critical value for range is y equals -4. So y is going to be greater than -4, and also y is going to be less than -4. That is our range. And in set notation, we have y is an element of all real numbers. However, y cannot equal -4. And finally, we have in interval notation -infinity, comma, -4, union 4 comma infinity. So that's going to be that problem worked out. Okay, next one here. Again, similar to problem 14, if you can work this out to get this what I would do is I would divide both the numerator and the denominator by -2, because if you do that, you're going to end up with x. So what you're going to get is 4x divided by -2, you get -2x, and we're going to have minus 13 over 2, or you can say minus 6.5. That might be an easier way to look at it. And then the denominator, you'd be left with x plus 3, and then work with that. Okay, now 17 through 20 we're given the graphs, and we're trying to use from the graphs write the function in that standard form, and we are given a center value here, and our center value here is going to be the point, make sure I get this right, looks like 3 comma 4. So that's 3 comma 4. So this means that our horizontal asymptote is going to be y is equal to 4. Our vertical asymptote is the equation x is equal to 3. So that means in the world of h comma k, I'll put that h comma k, x being 3, that means that h is equal to 3. It's really the value. So 3 comma 4, which is already done. So that means that our basic form for this function, I'm going to put this over here, g of x is going to be equal to a, we're going to figure out a in a little bit, times 1 over x minus 3, that's h minus k, plus 4. Now it's a matter of determining what the a is. And what you look at is, we would normally, for the parent function, have this point here just 1 to the right and up, but we notice we have 3 of those, so that means that a is going to be equal to 3. I'll write this here. So this tells you a is equal to 3, because that would be 1, 2, 3. A is equal to 3, which goes right over here. And that's going to be our answer. It's in that basic form. Okay, for number 18, I don't want to get in it. We have the form 1 over b again, and in the denominator again. As what my preference would be that you instead write this in the form a times 1 over x minus h plus k. That's what I would prefer that you do. I think it's easier to do, and that's the way I'd do it. Next, 19, write the function whose graph is shown. Use the form g of x equals 1 over b times quantity x minus h plus k. Again, I'm going to use the authority vested in me to have you write this as 1 over quantity x minus h plus k. So let's look at it that way. First of all, the center is the point. I'll just draw that arrow here. So center is at the point 3, comma, -1. So what that means is I'm going to start out with g of x equals, I don't have what a is yet, so I'm just going to write a here. We're going to have 1 over x minus h, which is going to be x minus 3. And we're going to multiply, we're going to add to that -1. Okay. And it looks like we are in the proper place, so it's a matter of just getting the right value here of where this is. So it looks like if we go to the place 1, instead of 1, we are half of 1. So to me, that looks like 1/2. So a is equal to 1/2. So I'm going to rewrite this as g of x equals 1/2 times quantity 1 over x minus 3 minus 1. And that's really all there is to it. I'm trying to see if there are some key values. If they're according to what's on the graph here, if we go to enter 0 for x, we should get a y-intercept of a little less than 1. So I'm just going to test that. G of 0 is equal to 1/2 of 1 over 0 minus 3 minus 1, which is going to be 1/2 of -1/3 minus 1, so that's going to be -1/6 minus 1, which is 6/6. So we're going to get -7/6, which seems like it probably is a fairly good match here if we're going. So this is going to be right here our correct answer. And let's look at number 20. It looks like we're going to have a is negative. Our center is going to be here at, it looks like, -2, comma, -4. Is that right? -2. And just work with there. A is going to have to be negative, so I'll just leave it to the viewer for that one. I hope it's been helpful. I thought this was kind of fun. Good luck, and as always, thanks for viewing.